Oh, hello. We're going to look at a mechanism in this module, and it's called Aromatic Electrophilic Substitution. Over here is a benzene ring, and the benzene ring has alternating single and double bonds in the carbon. These alternating double bonds have electrons in their hybridized sp2 orbitals. So if this molecule lies flat, like a planar molecule, the electrons in these pi bonds are up and back and available for reaction, which is what we're going to do. We're going to increase the length of this, increase the size of this molecule. We're going to make an attachment here. We're going to knock off a hydrogen and replace it with a 2-carbon chain. Now, in order to do that, we need some functionality on this 2-carbon chain. So we're going to start with a halogen, a chloride that's attached here. Now, at this moment, let me tell you, these two molecules are not attracted to one another, and nothing's going to happen, because I just got finished saying that there's electrons available, negative charge. And we know that chlorine, which sits in the top right, is electronegative. So as a matter of fact, you could summarize that these repel each other for the moment. But we're going to do something important. We're going to add a catalyst. The catalyst we're going to use is AlCl3. And the role of AlCl3 is in step 1 of this mechanism, where what happens is AlCl3 pulls chloride off of this hydrocarbon, and it's going to leave a carbocation intermediate. So the next step after the catalyst pulls chloride off is we have ourselves an intermediate. This carbocation is extremely unstable. It's not going to last any long amount of time. It has 3 bonds to carbon and a positive charge. If you will, it's like you're running and you're about to leap over a hurdle. When you're running, you're on the ground, you're stable. After you've hurdled, you're on the ground stable. But for a moment, you're in the air. You're not stable. You're not expected to float. That'd be bizarre. But instead, you're going to fall back down. Well, this is not stable. This is the intermediate. This is up over the hurdle, about to react and become stable again. This is going to attack right here. It could have picked any of the 6 carbon sites to do it, but it's going to attack a carbon in the ring. What's going to happen is a pair of electrons will swing out of that pi system and form a new bond. So we're going to have a carbon, carbon, carbon now with our new bond. That's going to mean that this carbon has 4 bonds, single, 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 and then this swings out for a single. That's going to make this carbon on the top of the ring, carbocation, 3 bonds, positive charge. That's unstable. So in the next step of this mechanism, what's going to happen is hydrogen is a good leaving group. The hydrogen is going to leave. When the hydrogen leaves, the pair of electrons swings back over, and we have, if you will, regenerated our alternating single-double bond system here. Let me do this with my hands and show you. This comes in, forms a new bond. H plus leaves. The bond is regenerated. Let me finish this up with a couple of details. I'm going to go ahead and show that H leaves as a proton, H plus, and when that occurs, H plus is going to come near the catalyst, and it's going to join up with chloride. So when this is all done, HCl will be formed, and as organic chemists, we're not too concerned. It's not our organic product, but our catalyst is reformed. We're left with AlCl3.